Hello, good evening, what's up, and welcome back to another 1001 MSc online video tutorial series. My name is Brock Grant, and today we're going to be going through composition of compounds and chemical equations. Now, something I'm sure that you guys have noticed already, for those avid viewers who have been watching all of the videos up to date, I've put one of our little stressed owl symbols at the front here. This module is hard. This module is very full on. We're going to be covering a lot of content at a very fast pace. So I will most likely be breaking this part into two sections. So let's hook into it. So as you can see, we're covering a lot of material today. We're going to be looking at the mole and molar mass, what that means. We're also going to be looking at percent composition, different formulas, different equations, how to balance them, and oxidation-reduction reactions. So the first thing we're going to cover is the mole. Now, the mole is an incredibly important unit in and amongst chemistry. And what the mole is it is a unit of measurement that expresses the amount of a chemical substance that we have. And it is expressed by the formula moles is equal to mass over molar mass. Learn this formula. Learn the hell out of it. You should be able to recite this upside down, back to front when you're half asleep, okay? This equation right here is so incredibly important that I cannot emphasize it enough that you must know it. I will guarantee my life on it that you will be examined using moles at some point in your university career. You need this. Here is why we need to use moles. Here's what it is and why we use it. So because atoms are so tiny, okay, and they're so small, they're so tiny, we essentially use the unit moles to simplify how much of a particular substance that we have. So this is why we don't look at mass, we use moles, because as we remember from our atomic theory, that different elements and different atoms weigh different amounts. So we use the mole to sort of unify them all, so we can use its mass to determine how many atoms that we have. Now, this number here. So this number, 6.02 times 10 to the power of 23, is known as Avogadro's number. That is an incredibly important number. It must be memorized. The good way to think about the mole is that it's sort of like a shortcut method for us. So it works the same way that we use 1 dozen. So how we say, look, I've got 1 dozen eggs. You should automatically sort of translate that in your mind to, oh, that person has 12 eggs. The mole is the exact same principle. If I say, oh, I have 1 mole of oxygen, that tells you that I have 6.02 times 10 to the power of 23 oxygen atoms. So again, what's the point? What's the point of moles and Avogadro's number? Why do we care? Why do we want to use them? The answer is that, again, Avogadro's number, which is 6.02 times 10 to the power of 23, is sort of like a bit of a translator. It helps us to convert moles to number of atoms. That's really important. So if a question states, if you have X amount of moles of a particular substance, how many atoms do you have? You use Avogadro's number to convert between them. Now, we look at the molar mass because the equation for the mole, as was written before, was moles is equal to mass over molar mass. So the molar mass is essentially, it's the exact same as the atomic mass, but it's represented in grams. So, for example, if we have a look at oxygen, so if you have a look at oxygen on your periodic table, it will look like that, except of course the atomic mass will be inside the box. Now, it's so important to understand this in that, yes, that is the atomic mass, which is in AMU, but the unit for this number can also represent 15.9994 grams per mole. So what does that number mean? What that number tells you is that if I had precisely 1 mole of oxygen, so if I had 6.02 times 10 to the power of 23 atoms of oxygen, it would weigh precisely 15.9994 grams. Now it's the same with carbon. If we have a look at carbon, it has a molar mass of 12. Now, if we have a compound, so if we have, we know its formula, so this is its molecular formula, what we can do is we can calculate the molar mass of that entire compound by just simply adding them together. So for example, if I had O2, so if I had 2 lots of oxygens, it would be 15.9994 times 2. Another example is that if we've got aluminium oxide, so we've got Al2O3, so we can see here that the molar mass of oxygen is 15.9994. Rounding that to 16 is okay, that's fine. And aluminium, which is 26.98154, so you can just round that to 26.98. And what we do is we multiply the molar mass of aluminium by 2, because we've got 2 aluminiums, and we multiply the molar mass of oxygen by 3, because there are 3. And what we do is we simply add them together. So that means the overall molar mass of our aluminium oxide is 100.56 grams per mole. So again, to translate that, it means that if we had precisely 1 mole of aluminium oxide, so if we had 6.02 times 10 to the power of 23 atoms of aluminium oxide, it would weigh precisely 100.56 grams. Now, another sort of good study tip with this is to make sure you understand what these individual parts are. This is why I'm putting a lot of emphasis on this, and you understand your units. So if you understand that the units for molar mass are grams per mole, you will know how many grams it will weigh per mole. It's the same with density, how density is mass over volume. You will know the mass of that substance per unit volume, okay? It's the same thing. If you understand your units, it will help you a lot in your examinations. Now let's move on now to percent composition of compounds. Now this is a very important and often a very sneaky question that can catch a lot of students off guard. But what the percent composition is that it is the percent of mass of each element that forms the total mass of that compound. So if we know how much that compound weighs, what is the percent weight of one element versus another? So let's look, for example, at water over here. So the first thing we want to do when we're looking at percent composition is we want to calculate its overall weight. So with water, we've got obviously 1 oxygen and 2 hydrogens. So we calculate the overall mass. So with hydrogen, it is 1 gram per mole times 2 because we have 2 hydrogens, plus 16 because that is the molar mass of oxygen. And we add those together to get 18. So that means that water will weigh 18 grams per mole. Now, that doesn't answer our question, but we're looking for the percentage. So the next thing we do is we find the percent mass of each individual element. So we look at, first of all, of oxygen. So oxygen weighs 16 grams. So we go 16 grams per mole divided by 18 grams per mole, which is the total mass of water. And we will get 89%, or it will be 0.89, to which you multiply that by 100 to give it to you in percentage. Now, it's the exact same with hydrogen. 2 grams per mole, because remember we have 2 hydrogens, divided by 18 will give you 11%. So that means with H2O, 11% of that raw mass is dedicated to hydrogen, while 89% is dedicated to oxygen. So let us now move on from percent composition and let us now compare empirical versus molecular formula. So the molecular formula is the true formula. That's the one that we have been using essentially this whole time. So this is like Al2O3, and we're looking at aluminium oxide. That is the molecular formula because it tells you the entire compound. It shows you all of the different elements that comprise that compound. It gives you all the information. However, our empirical formula is known as a simplest formula. So it gives you just the smallest whole number ratio of the atoms that are present. So this one is a lot simpler to write down and use. So let's look, for example, at glucose. So the molecular formula for glucose, and again, you don't need to memorize glucose, is C6H12O6. Now this is your molecular formula. It tells us all of that in sufficient detail. Now, if we compare this to the empirical formula, we can see it's just CH2O, because there are twice as many hydrogens as what there are carbons and oxygens. So it's based on just simply the whole number ratio, not on specifically identifying how many of each atom, or how many of each element we have. Now, if we do need more detail, more information, we can use percent composition, like we covered just before, to convert the empirical formula into its molecular formula. So that's the good thing too, is that we can work between the two, so we can convert one into the other. So now that we've looked at percent compositions and the difference between a molecular and empirical formula, here are the steps that you need to perform to convert an empirical formula to a molecular formula via the use of percent composition. So to do this, what we do is that no matter what your compound is, assume that the starting quantity is 100 grams. Now the reason why we choose 100 grams of a particular substance is just for mathematical simplicity. Because remember, what we're trying to do is convert our ratio, which is the empirical formula, to our molecular formula. So once we have our molecular formula, we can then move next step from there in terms of whatever the question is asking. So step 1 is to assume 100 grams of a particular substance. Then what you do is you convert the grams of each element into moles, because remember, we cannot compare masses. We can only compare moles. So once you've converted the mass of each element into moles, what you do is then you divide all the moles calculated by the lowest molar value. Okay? So essentially, you want to try and follow this little schematic here. And again, just keep an eye out for video 2, where we're going to run through an example. So if you're given the mass percent of a particular element, you assume it's 100 grams. You then use the atomic weight, which is your molar mass given to you on the periodic table, to calculate the moles. And then you'll be able to see the molar ratios by dividing all of them by the lowest molar number. So now what we're going to do is we're going to be talking about chemical equations. So a big thing you need to keep in mind when we're looking at our chemical equations here is the law of conservation of energy. So this law is incredibly important in both chemistry and physics. And essentially what this law tells us is that in any reaction, okay, atoms are not created nor destroyed. They are simply converted from one form to another. Now that is very important to keep in mind, because what that means is we've got our reactants and our products, that as we look around on our reactants, it must have the same number of atoms in terms of aluminiums, ions, and oxygens on the reactant side, so over here, as it does on the product side. So what we can see here is that we've just had a single displacement. So the aluminium has swapped places with the iron. So it wasn't as though aluminium or iron just disappeared. They just simply changed their form. Now something to keep in mind is that the chemical equations, like we've got written up here, it's a shorthand description as what is happening at a chemical level. So it just gives us a lot of information on how these things are reacting. But again, you've got to interpret and balance this equation. So what balancing means is making sure you have the same number of elements on the left as you do on the right. Now, a side note here. Every single chemical reaction and equation in the history of ever will always balance, okay? If it won't balance, it doesn't exist in nature. So once we have the equation balanced, this is when we can really get a lot of information from the chemical equations, such as the amount of reactants and products, the number of moles, the mass of each, etc., etc. So it's very important that whenever you are answering a question on your exam involving a chemical equation, that you always check to make sure it's balanced, because if it's not balanced, your answer will be wrong. So now we must ask ourselves, if we are given an equation that isn't balanced, what do we do? How do we balance it? So let us look at a demo equation that we have here. So hydrogen plus oxygen gives us water. So the first thing that we need to do is we need to convert this into its chemical form. So we can't just write hydrogen, we need to write it in a molecular way. So H2 plus O2 will make H2O. Now we look at our raw elements here and we go, are they balanced? So what I mean by that is, are the number of elements on the left-hand side equal to the number of elements on the right-hand side? So as we look here, we have 2 hydrogens on the left and 2 hydrogens on the right. Happy days. But the problem comes with oxygen, because we only have 1 oxygen on the right, but we have 2 on the left. So this means it is not balanced. So we must balance this before we can do anything with this chemical equation. So the first step I recommend doing, and I recommend doing this whenever you balance an equation, and preferably do it in pencil. Pencil can save you a bit of time, is to draw a table. So what I do is I just go left, right, and you just write down your elements on the side here. So we have hydrogens and we have oxygens. So how many hydrogens do we have on the left-hand side? So we've got 2. How many hydrogens on the right-hand side? We have 2. How many oxygens on the left-hand side? We have 2. How many oxygens on the right-hand side? We only have 1. So this gives us a reference point. It tells us, okay, what do we need to change? Now, what we do is to balance these elements, what we can do is we can change the coefficient. Now, this is an important step I want you all to be comfortable with. When you are balancing a chemical equation, you can only change the coefficients. So looking at our example above, how we need an extra oxygen, I cannot just draw a little oxygen like that, okay? Because that is incorrect. You can only change the coefficient. So what we do is we look back at our table, so we can see that there are 2 products on the, we have 2 oxygens on the left, 1 oxygen on the right. So what makes sense, what we need to do is we need to put a 2 in front of H2O, because this will increase our total number of oxygens. Because we changed the coefficient, whenever we change or tinker, do anything, always redraw your table. So what you do is you draw another table and you do a recount. Now, apologies here, I've accidentally made a bit of a typo here. I've got them written the wrong way round. So I'm very, very sorry about that. Now, as we do a quick count again, 2 hydrogens on the left, there are 2 oxygens on the left. Now, as we recount our water, we have 2 lots of 2 hydrogens. So we have 4 hydrogens total. So we have 4 hydrogens and 2 oxygens. So, we're overshot, okay? So now our hydrogens aren't balancing. That's okay, because what we can do is we can just simply place a 2 in front of our hydrogen. So 2 lots of H2 will give us 4 hydrogens, 2 oxygens on the left, and then 4 hydrogens on the right, 2 times 1, 2 oxygens on the right. And therefore, our equation is now balanced. Now, again, this may take a couple of steps. I chose water because it is a simpler, it is a more simple example. However, you may need to repeat steps 2 to 5 a few times until you get the correct answer. Now let us look at different types of chemical reactions. So the first one is a combination reaction. So this is where two reactants combine together to give one product. So we can see here we've got two magnesiums, two oxygens, and they combine together to form magnesium oxide. The next one is a decomposition reaction. So a decomposition reaction is where a single reactant is broken down to give more than one product. We also have a single displacement reaction. So what this means is this is where one element in a compound is swapped to replace another element of one compound. So we can see here we have zinc with hydrochloric acid, and the hydrogens and the zincs swap places. So this is a single displacement reaction. And of course, a double replacement reaction is essentially like a dance. So it's where you've got two couples dancing and they swap partners. So hydrochloric acid and sodium hydroxide swaps. So we've got the sodium and the chloride and the hydrogen and the OH to form sodium chloride and water. Now the last one and the most tricky of all is the oxidation-reduction reaction. So what this reaction means is it is just simply a reaction that involves the transfer of electrons. That's it. That's all it is. It is just the movement and transfer of electrons from one compound to another. Okay, so now we're going to start talking about the oxidation-reduction reaction. So this is a very tricky topic, and a lot of students get confused and very lost by this when they don't have to. Okay? If you understand the basics of what's going on in a redox reaction, why we do it, and the steps involved in in solving any problem with redox, redox is a piece of cake. Okay? So I'm going to explain what redox is and how to solve a redox reaction that will make you get it correct 100% of the time. So the first thing is obviously looking at redox. So redox is a reaction that involves the transfer of electrons from one element or compound to another. Now we see redox on an almost daily basis. We see it in rust. So if you've got a bit of rusting metal, that is done by redox. If you're getting older, you're all aging right now. Aging occurs by a type of redox occurring inside of your cells. Now that's a little bit more complicated. We're not going to go into that, but redox is involved in our cells. We see it when we breathe. It's everywhere. Now, what we're going to be talking about when we talked about redox is something called an oxidation number. Now, this is another reason why I have been very persistent throughout these previous modules and videos on being able to calculate the charge of a particular element. Okay, so looking at its valence electrons and looking at if it's got a charge of -2, +6, whatever. Okay. Now, what this oxidation number represents is it will show us how many electrons are lost, gained, or nothing has changed. So it's the representation of a charge. Now, if you have a positive oxidation number or a positive charge, it means that element has lost electrons. If it's a negative oxidation number, it means it's gained electrons. And if it's neutral, so if it doesn't have a charge, it means there's no movement. So sometimes a question can be written for students saying, balance the following equation. It won't identify whether it's a normal equation like we did before, or whether it's a redox. Because it could say balance the following equation, and it's a redox equation, which we need to do slightly differently. So the thing you have to do to differentiate between the two, to see whether it's a redox reaction or a different kind of reaction, is look at the oxidation number. Look at the charges. Does the charge of a particular element change? If yes, then it's redox. Straight away, full stop. If there is no change in the oxidation number in a reaction, it is not redox. It's simple as that. Now, a very important thing I want you guys to learn is oil rig. So whenever you see a redox question, redox equation, anything with redox, straight away you should write down oil rig. Now, another way this is also written and taught is Leo the lion goes grr. If you want to use that one, that's fine, but be my guest. I personally prefer to use oil rig because I find it easier to remember. So with oil rig, it is oxidation is the loss of electrons. So OIL, oxidation is lost. Reduction is gain. So reduction is gain of electrons. Now, again, what you must remember is, and this is again an area where students often get stuck, is they go oxidation is the loss of electrons. So if an element gets more negative, then it means it must be oxidized. And the answer is no, because you remember that oxidation is the loss of electrons, and electrons are negatively charged. So that means that if something is being oxidized, it means it's losing those electrons. And if it's losing those electrons, it means it's getting more positive because it's losing those negative charges. So a lot of people get confused that if something gets more negative, it means, oh, they're losing something, it must be being oxidized. And the answer is no, it means it's being reduced. Because if something is being reduced, it's gaining electrons, and those electrons are negatively charged. Now let us explore what an oxidizing agent is. Now, a lot of people get confused here as well, and this is a bit confusing, so bear with me. Now, an oxidizing agent is a substance that causes the oxidation of a substance by gaining the electrons. So, for example, if we have something that is being oxidized, so if we have something that is losing electrons, the oxidizing agent is the element or compound that gained those electrons. And you can think of it like this, is that yes, okay, if we've got a compound that is being reduced, it is thought of as the oxidizing agent in that if it wasn't there to steal that element or compound's electrons, that particular element or compound could not be oxidized. So because that compound was being reduced, it enabled that compound to be oxidized, which is why the compound that is being reduced is called the oxidizing agent. So the same is said of the reducing agent, in that the substance that causes the reduction by donating the electrons, which is the compound that is being oxidized. So if you've got something that is being reduced, it is thought of as the oxidizing agent. Whereas if you've got something that is being oxidized, you can also call that the reducing agent, because the compound that is being oxidized, it is donating those electrons and giving them to the compound that is being reduced. Which is why if something is being oxidized, it's also called the reducing agent because it's donating those electrons, allowing that compound to be reduced.